Hi, everyone. Ryan and I will be talking about how Twitter fused Elasticsearch with neural networks to identify personal data. So before we dive into the work itself, a quick introduction about the speakers. I am Rakshit Wadhwa, the one on the right, and I'm a software engineer at Twitter. I have been working at Twitter since last 2.5 years now, and I am part of the privacy platform team that builds tools and services for data protection and privacy. Along with me is Ryan Turner, the one on the left, and Ryan is a senior machine learning researcher at Twitter. He has been at Twitter since past 2 years and is part of the Cortex team. Cortex teams provide machine learning solutions and expertise for various projects across Twitter. Let's begin with an introduction about what are the problems that we are trying to solve here. So the main problem that we are trying to handle here is the accounting for the personal data in Twitter systems and then tracing it, how it originates and flows through various Twitter datasets. The problem is complicated because of the microservice architectures across the company. This leads to a distribution of data across different teams and services. As a result, the accountability for the data privacy is distributed throughout the organization. To understand this distributed data, we need a common language or taxonomy to refer to the data columns. We call this tagging of the data, or also known as annotation. Note that this taxonomy with which we annotate the data was developed with the effort of engineers, product managers, and legal teams so that it can serve all the three verticals. The two main challenges in tracing and accounting personal data are: first, the data is continuously growing and getting distributed to various datasets and storage systems. These datasets and storage systems can be very non-homogeneous. Second, the data privacy and governing policies are continuously evolving, and Twitter as an organization needs to adhere to these ever-changing policies. Keeping these challenges in mind, we started with the following goals. Primarily, we wanted to understand what data exists in our systems, the sensitivity of that data, and the purpose for which the data is getting used across Twitter. Our secondary goal was to utilize this knowledge to also optimize for our storages, understand the usage pattern for different kinds of data that we have in our systems, and to improve overall data security and data handling situation at Twitter. The ideal solution to solve such a problem could have been to use a standard taxonomy within the schemas themselves. That is to name the columns with personal data types directly from the taxonomy. This might have worked when you were building something from scratch, but changing schemas for the existing data sets would not only lead to heavy refactoring across different consumers and producers of that data, but would also be a long and painful process, which might even result into downtime for different services. And above all, this could be an error-prone process and is a heavily manual process. Now coming to the solution that we actually adapted. Instead of changing the column names or field names of the datasets, in the schema itself, we decided to tag or annotate the columns with terms from the standard taxonomy. This has multiple benefits. It is done on top of the datasets and hence doesn't require any refactoring to the actual datasets themselves, so the underlying code keeps on running as it is. This also means no downtime for the existing tools or services. Further, this design allowed changing the annotation or adding multiple annotations to the same field, which would not have been possible if we made changes to the schema directly. This also means that we can automate annotation process to a major degree by building a recommendation service for these annotations. So to make the annotation process easier, we built a recommendation engine based on probabilistic model on top of Elasticsearch. Note that such a system is not only useful for any company handling lots and lots of personal data, but also for any time you need a text-based lookup with quantified uncertainty. We'll go into much more detail about the recommendation itself and how the recommendation engine is built in the second half of this presentation. To make it more concrete for now, here are some annotation examples. Let's say that we have a dataset named profile that has a column called ID, which has column description as unique identifier for the user. Here, the column is annotated as user ID. In the absence of the annotation, it is very tough to determine exactly what the ID means for the dataset. And another example could be a dataset, let's say it's called timelines, which has a column name called user ID, which actually stores Twitter handles in it, and hence is annotated with username. So the column name is user ID for the schema. So overall, having an annotation recommendation service not only increases the development velocity, it also helps to maintain the quality of the annotations through benchmarking and auditing previously annotated data. Here are a few numbers to understand why we need a recommendation engine rather than manually annotating from the scratch. We have 504 terms in our standard taxonomy. We call these terms personal data types. There are more than 2 million fields or columns spread across more than 100,000 data sets and a dozen of data stores. These 2 million fields need to be annotated with these 504 personal data types. When you're dealing at this scale, having a recommendation engine for these personal data types can be very, very useful. Now, a quick overview of the recommendation engine before we go into more details. Twitter manually created a taxonomy of 504 possible annotations. This taxonomy was created via combined efforts of engineering, product management, and legal teams. Engineers and product managers then use this taxonomy to manually annotate datasets for a while, and around 30,000 columns were annotated this way. This became a basis for creating a recommendation engine, which was used to annotate over 2 million columns spread across 100,000 datasets with these 504 annotations. Note that the final decision of the annotation is still done by the user, as these annotation needs to be accurate due to various privacy and data governance policies, but having recommendations make it much, much easier because we boil down from 504 annotations to just maybe 10 recommendations. And now a quick overview of the high-level architecture for the annotation recommendation service. At the bottom of the architecture, you'll find the data collection engine that collects columns and personal data type mappings, as well as other metadata across the data sets which are already annotated. This essentially acts as a training data for recommendation engine. The recommendation engine is based on a probabilistic model on top of Elasticsearch. And this recommendation engine interacts with our internal services and tools through the REST APIs. These REST APIs interact in our tools like metadata store, code review tools, linters, etc., to make it easy to annotate the data as well as search for already annotated data. I'll now hand it over to Ryan to give a more deep dive into our recommendation engine. Over to you, Ryan.
Hello, I'm Ryan. I'll take over for the technical part of the system for how we built this recommenders system for annotations. Yeah, so basically the first step in building any automated recommender system is that you need a ground truth set. So we had just a subset of annotations that were manually labeled. We had a lot of manually labeled data, but we wanted to make sure that we trusted all the ground truth data that was going into the system for Elasticsearch, and then the follow-up calibration system. So we had a training corpus of 70,000 different annotations. So these are different columns of data across all the different data sets that we have that were labeled to exactly which type of personal data it was out of the 500 different types. And these were 700,000 that were labeled by labelers that we were confident that they were good ground truth. So that's like the first step. That's how we got everything we needed there. And then what we needed on top of that is we needed features. So what we did is we augmented it with the metadata as was described in section 1. And all this metadata are things like the data set name. So like what data set is that column part of? It will have a name, it'll have a description, it's free form text. The column has a name. As you know, columns and data sets always have names. It also have a column description, again, as like a free form text, as a few sentences, as shown in the examples in part 1 about describing what that column is. And all this stuff is just a bunch of freeform text. As such, doing this recommendation using Elasticsearch was a natural way to get that first iteration of in our pipeline for the predictions. And here I'll describe the inputs and the outputs as well, because again, we're building any ML system. This is like the key. These are like this is the key ingredient. You need to well define what's your input, what's your output, right? So the input here being these three forms of free-form text, of data set name, call names, then a sentence or two on its description, and then the prediction being one of the 500 different possible annotations on what the type of personal data. So this is what's known as a multi-class classification problem. So there's just one of 500 different possibilities as the output. And this is how we frame the problem, which is, in my opinion, I think is usually the key and most important step of any sort of applied sort of ML work of how do you frame the problem. And this is it here. This is our framing of the problem. So again, here we have this examples. So we have data set name, column description for each example. So each of these is basically one row of data in our corpus. So on the left in the non-bold sections, these are the examples of the inputs. So we're supposed to make the prediction based on, okay, it was a profile, it was in a column named ID in a data set called profile, and it's, this description, unique identifier for the user, right? And then one of the 500 possible classes is user ID. And, that's the correct prediction. That's the ground truth prediction for this row. And then here's another example where the ground truth prediction is username, which is, there is it looks like some distinction between user ID and username. It's just, somewhat subtle. So the system does have to be able to make those distinctions between these two subtly different classes between a user ID and a username based on the information on the left, which is all this metadata. So, this is not a trivial problem, but as we see in the later slides, we still do get, pretty good, decent performance on it, this case. So, okay, so basically, as we were saying earlier, there's two different steps to this process. Step one, reduce this to a text search problem, and then in step two, we're going to build a classifier that we want to make like calibrated probabilities for the predictions. So here we're talking about step one. So basically what I have is a machine learning type problem is I have a classifier, but we need to reduce that into something that is good for Elasticsearch, because as I said, we want to do something that leverages those existing solutions. So basically we had to turn that corpus into these inverted search indexes. And a lot of these sort of systems like Elasticsearch is based on documents, right? You have some keywords and it returns a document, right? But in this case, we don't have documents, right? So we have to create synthetic documents for every possible annotation needs to correspond to a certain synthetic document, right? So basically, the way we do that is we concatenate all the metadata for all the examples in the training set for the case we have the same annotation. You concatenate all that metadata together, just simply with commas. You concatenate all that text together, and that's a document. And then in the test phase, we do Elasticsearch queries for those keywords, and if that document comes up, then that's then we predict that's the annotation. And other examples in a more pictorial form of how that works. And then we also, one of the goals of the project is to have somewhat calibrated probabilities for our confidence on how confident we are in each of these predictions. So then the second phase will be the calibration model. So here's a diagram describing visually the last slide here. So this is the text-based features. So basically, we take all the examples in the training set where the annotation was username, and then just sort of concatenate together the metadata with commas. And these are all what I call the synthetic documents, right? So in test phase, you might find you'll come across a new column of data where the metadata is going to have feed and handle in it. And Elasticsearch will pop up. Okay, this synthetic document corresponds with that column, and then we know, okay, username. Right? So that was the first step, and then the second step is the calibration model, because Elasticsearch doesn't return probabilities. Is one issue, and that was one of the goals. It returns this IDF score, but we wanted to convert those to probabilities. Secondly, another issue is that we weren't exactly sure what the best Elasticsearch query was. So what we actually do multiple Elasticsearch queries, and then this step 2 model actually merges them together to give a probability for each. Based on the results of each query, all of those go into the step 2 model, the calibration phase, and it provides a predictive probability, a classification for the full set of 500 different annotations. So a big key in building calibration models in ML systems is that you want to have a held out model if you want to be well calibrated. So 20% of the data was held out, not given to Elasticsearch for indexing. And so Elasticsearch was able to see 80% of the training data, and then another 20% was held out for training a classifier based on the output of Elasticsearch. Basically, the results for Elasticsearch become basically numeric vectors for each of the 500 possible cases. You get the Elasticsearch score. A lot of annotations will have score 0 because they don't return in the search results of Elasticsearch at all. And then everything that does appear in the search results will have whatever its similarity scores from Elasticsearch. So we have a 500 dimensional feature vector from Elasticsearch. It's a sparse 500 dimensional feature vector. And then we have I think we have 4 of those because we do 4 different variations of different queries. So we have 4 times 500 dimensional matrix for making a prediction on. So we fuse together all these different Elasticsearch queries, and basically the feature vector coming into the system is a 4 by 500 dimensional sparse matrix, and then the output of the calibration model is a probability distribution across 500 different classes. So it's a 500-way multi-class classification. So at this point, it's a somewhat standard problem to be looking at. We train this on the held out 20%, and it's we try a lot of different models. So we're not just using neural net model just because it's fashionable. We're using it because it's something that we found to work the best. And here's a visual representation of this. Here we have the query, and it generated a bunch of different types of variations on that query. Elasticsearch returns a bunch of results for each one, and then we have this neural net model that fuses them all together to a final classification. And it's just a classification problem, so we try a few different ways of evaluating it. Again, we have the typical top 10 accuracy. So basically, in the top 10 search results that get returned, do we see the correct ground truth annotation in that top 10? And so here, higher is better. We see again, neural network works the best, but of course, random forests are another. It's often another top performer across many different problems, and we see it performing similarly. But that doesn't evaluate the calibration of the probabilities, which is something we were also interested in. And for that, we use what's known as the log loss. And reassuringly, it returns pretty similar results. The top 10 accuracy is basically the same story. So you don't have to make a hard decision on which metric do we actually care about more. They're both qualitatively similar, and that we also see that the neural network has the most the most calibration because it's the best log loss out of every model. And of course, log loss, because it's a loss, lower is better, and we see the best log loss from the neural net. And again, good performance from the random forest as well, but not quite as good. So that's how we built the system, and we see that it's been in use for over a year, and 74% of the annotations over that period have been built or come from that recommender system. A lot of users are so familiar with the different annotations that maybe they don't even bother using the recommender system, and they just know exactly what the right answer is. But you know, for 3/4 of the users, they are not that familiar with that taxonomy of 500 different annotations, so they will use the recommender system to help determine that. The final system, the final recommendation still does come from the human data scientist, because there is compliance aspects to this, but we're seeing that this system is very useful for them to make that determination. And we have Elasticsearch forming the first phase, and then with some classic ML models on the second phase of this system. And it's a very good use case of both, and consequential use case of both. So in conclusion, we see that this is a powerful combination for using these ML models and Elasticsearch. It's a big problem we have, and a lot of companies have, about annotating these legacy data sets, and this solution, which leverages Elasticsearch, has been a big part in fixing it and building solutions that we have the correct annotations of personal data to correctly annotate everything. And inserts a lot of use cases for auditing and allowing user teams to understand all the sensitivities and assign permissions, and has a lot of impact. And I will leave it there. And thanks for listening.